In today's class, we'll discuss about the emission measurement. Um, First of all, why we need to measure the emissions? So this is the first question. So basically, emissions we need to measure to know that whether your vehicle or the engine is meeting emission regulations or not. In the previous class, we already discussed that the emission regulations means so you need to quantify how much emissions are coming from the vehicle or the engine. So how can you quantify? So to quantify that one, you should measure properly that one. Okay, so that's the main reason why you are measuring this one. The second reason is that so we want to understand the combustion phenomena that is occurring in the engine actually. So how can you measure that one? So that can be measured through by measuring the emissions. What are the emissions actually? The emissions are nothing but the combustion products. So by measuring the combustion products, you can interfere about how well the combustion is occurring. So if you want to improve the engine performance or the combustion performance based on these emissions, you can take some decisions. So these two are the main reasons due to which we are trying to measure the emissions actually. Okay, so now what kind of emissions we are measuring? So in the previous class, we already discussed that the exhaust of the IC engine is majorly consisting of THC, the unburned hydrocarbons, then carbon monoxide that is CO, then nitric oxides NOx, then smoke, and then sulfuric oxide and carbon dioxide. Okay, so in our syllabus we are having the details about the first four, so we'll be discussing about the how to measure the first four components. Okay, so this will tell you what are the techniques what you are using to measure the emissions. So when it comes to for unburned hydrocarbons, the technique what you are using is a flame ionization detection method. Okay, so when you go for carbon monoxide, we are measuring it through a technique what is known as NDIR method. So non-dispersive infrared radiation method. Okay. Then oxides of nitrogen. So it's NO, NO2 together. It is known as NOx. So this we are measuring through chemiluminescence method. Okay. Then the fourth one, smoke, soot, or particulate matter, we are measuring through two methods. That is Ringelmann chart and Boss smoke meter. So now we'll discuss about unburned hydrocarbons. So first thing, the measurement of emissions for that matter, the measurement of any species concentration is extremely difficult task. It's not easy. Suppose that you want to measure temperature, the pressure, any forces, the sensors or sensing element is not so complicated. Suppose if you are taking the pressure, so there will be a diaphragm which will be directly sensing the force and then convert it into deflection, then that will give the pressure measurement. Similarly, a thermocouple will measure the potential difference or the expansion of a mercury column, and that will be converted into a reading. So it's nearly straightforward, those two are, but the concentration measurement is extremely difficult talks. Okay, so basically, when you are measuring emissions means you are trying to measure the concentration of a species in a mixture of the gases. Okay, these concepts are not only limited emissions but have much wider applicability in actual industrial applications. Okay, so you be remember that measuring the concentration means it's an extremely complicated task. Okay, so as when you're going through these slides, we'll understand that it is how much complicated. Okay, so first we'll discuss about the THC. So flame ionization detection method, FID method. Okay, the principle is that when you burn hydrocarbons to very high temperature and very rapidly, then the hydrocarbons will ionize, and because of the ionization, it will be liberating the ions and electrons. Okay. Now, if you are able to connect an electrical circuit to the reaction chamber, then what will happen? So these ions will hit a collector plate, will hit the collector plate. So because of this impact of the ions, electricity will be produced, and the amount of electricity that is being produced here is directly proportional to the number of the carbon atoms that are present in the unburned hydrocarbon. So this is the principle here actually. Okay. Now there are three factors are there here. Okay. So since we are discussing about the automotive exhaust gas, the concentration of THC in hydrocarbon exhaust gas will not exceed 10 percentage. Okay. Okay, the small percentage of the 10 percentage, when you even go for the burning of this fuel, this THC, the released temperature is not so high to take the temperature to the ionization levels. Okay. In a nutshell, what I'm saying that the small, very little amount of THC present in the exhaust gas will not burn to give sufficient amount of energy so that the THC will go to ionization level. Okay, so probably plus two you do understood that any molecule, right? First it has a translation energy, then it has vibration, then it has the ionization levels. Okay, no, sorry. First is the translation, vibrational, then the dissociation, then further additional chemical reactions, then you have the ionization. So there are so many levels are there. To cross each level, you need require certain amount of energy, right? Now, in the present case, when you are burning the THC alone, standalone THC, the amount of heat that is liberated will not take the species to that level. So to do this one, you require another fuel for the burning actually. Okay, so now what we will do, so you take another fuel, and to burn this fuel you require again air also. So you require three, so you require entire setup that will be having the an addition fuel and plus air. Okay, so this we'll discuss in the next slide. Okay, the number of the parts are, as I said earlier, so you should have a burner to burning this one, and then there is a fuel and the air and the regulators and the capillary tubes to control the flow and the pressure of these two systems, and a sampling unit to sample exhaust gas, and of course you should have electrical circuit to measure the current that has been produced. Okay, so these are the main parts. Okay, first, so this is the diagram. So please do remember that all this discussion, all these measurement methods, it can be asked for 12 marks question. Okay, so you need to make a proper diagram and proper explanation. Most of the time the diagram will carry 6 marks and the explanation will carry for the 6 marks. Okay, so first take a closer look at this diagram. So in the bottom side we are having the air, and here on right hand side the fuel plus sample are coming. So usually the fuel plus sample both will mix together and will be sending through this passage. Okay, now the air plus fuel plus sample 3 will mix together properly and it will be sent to the burner here. So this is the burner. Now there is a jet here, so here is the where the flame, the fuel will be burning, and THC will be going for the ionization. So now here we have the electrical circuit. This all is electrical circuit, and this is a collector plate which will be negative side, and the ions are positive, so the ions will travel towards the negative side. Now upon the impact here, the current will be produced, and this current will be measured by the circuit here. Okay, you can see that it is written as ion plasma. So we'll say, so how to differentiate between plasma and gas? The plasma is telling that it has certain amount of electrons, ions. If you take any matter, if that matter is consist of the even small amount of ions or electrons, then you tell it is a plasma. Okay, so usually it will be consisting of majority of gas plus certain amount of electrons or ions, then we'll call it a plasma. Okay, so when I say that is ion plasma, this region is consisting of ions plus the gas here. So a closer look of this part is shown here. Okay, so first we'll start from here, the air. So air we are sending through the filter. So the filter will filter the any impurities in the air. Then it is going to the regulator, and then through the regulator we are sending to the burner here. Okay. The second line will be corresponding for the fuel here. The fuel will be coming through solenoid valve. So this will be controlling the flow rate of the fuel. Then you have the regulator. Then the gauge here, the gauge means we are trying to measure the pressure of the fuel at which it is entering to the combustion, the burner. Okay, then it is going to the burner here. Now see, this line is the where we are taking the sample of the exhaust gas. Okay, the sample proof will be telling you that it is like a sample. We are taking the sample of the exhaust gas. So of course the filter is there. So this three-way valve. So you have the pump which will be used to control the pressure of the sample gas. So it is allowed to go through the T section. So in the upward direction, it will be travel to the capillary tube and went to the reaction chamber. So in the downward direction, we have the flow meter to measure the flow rate of this one. Now, so first thing is that air. So you require air for the. So you require this air for the burning of this fuel. Okay. Now this air, can you take atmospheric air? Whatever there in outside atmospheric air, you should not take atmospheric air, because the atmospheric air will be consisting a certain amount of THC. Okay, now if you take the atmospheric air without filtering or without any purification, now the THC in the air and the THC in the exhaust gas will mix together and you may get erroneous reading. Okay. Or in the sense the current that has been produced in the circuit will not reflect the THC that is there in the exhaust gases. So it will be reflecting you the THC in the exhaust gas plus THC in the air. So to avoid all this stuff, right, you need to purify the air and take this one. So you have to make sure that the air that has been using here will not contain any THC. Okay. Now the second point, what kind of fuel you can use here? Okay, again the same point comes here. Suppose that the fuel what I've been using here has again hydrocarbons, then it is again lead to the case confusion reading. Okay, suppose that in the fuel hydrocarbons are there, and now these hydrocarbons also will go for the ionization, and the hydrocarbons present in the exhaust gas also will go for the ionization. Then the current has been produced will reflect the concentration of the THC in the fuel plus THC in the exhaust gases. So that we do not want. So we want to measure only THC in exhaust gases. So preferably the fuel that you are using should not have any THC. Then the reading will be representing only the THC that is there in the exhaust gas. So what is the fuel that does not have any hydrocarbons? It is only hydrogen and helium. So these are the only two fuels which does not have any hydrocarbons. So preferably we'll be using the hydrogen. Okay. So indirectly, this air we are sending here, and here we are sending the hydrogen. Okay. So usually, if you get into details of thermochemistry of hydrocarbons with reference to ionization, they most likely will give ionization near at the 1500. Okay, not less than 1500. Okay. Now someone can question me, what about the remaining gases in the exhaust? CO also there. Can CO can go into ionization? What is stopping CO to go for the ionization? Why does only TH is going for ionization? So these are all thermochemistry calculations. It's already known that the ionization temperature for the CO is higher than that of THC. Okay, and similarly for nitrogen also. So in the exhaust gas, nitrogen also is there. Okay, so nitrogen also can go into ionization level, but the temperature limit for the nitrogen to go into ionization is nearly 7000 Kelvin. Okay, unless otherwise the hydrogen flame generates a temperature beyond 7000 Kelvin, the nitrogen will not go for the ionization. Okay, so there is no question that ions will be produced from the nitrogen. Okay, and similarly, since the temperature at which the ionization will occur for the CO, NOx, remaining gases more than the 4000 Kelvin. Okay, so you have to make sure that the hydrogen flame temperature will not exceed the or will not touch the limits of the ionization temperature limits of the CO plus NO plus N2. Okay, even in fact for the NO also, for the ionization to occur, it has to cross the minimum 5000 Kelvin or minimum 4000, sorry, it has to cross minimum 5000 Kelvin. Okay, so you should not go into that level of the temperature. So you should always maintain the hydrogen flame below 4000 Kelvin. So I tried to get this number from the internet, but it's not available. The exact ionization temperature for the TH is not available in the internet. So you can try to get this information. So this 1500 I'm approximating. But I know surely ionization temperature for the NO and N2 are nearly above 4000, above 7000 respectively. So now this last sentence, the regulators and capillary tubes are used to control the flow rate and pressure of air and fuel plus sample gas. Next, the calibration. So calibration means suppose that you are burning and the THC going for the ionization, and then you got the current also produced. Now suppose that 1 ampere of current is produced. Now you should be have some understanding that when 1 amp of current is produced, it will be representing you how many atoms of carbon in the THC. So that data you need to generate priori. So that method is known as the calibration. Okay. Okay, so how can you do calibration means you need to send known concentration of the mixture of the gases to the reaction chamber and measure the current produced and correlate that one with the concentration. So what I'm saying is that, so initially before starting the your experiment to measure the THC in the exhaust gas, first of what you need to do, so you prepare a mixture of CH4 0.1 percentage with N2. Okay, so you take N2 and CH4, mix this one with the ratio of 0.1 plus 0.99. So the mixture is consisting of only 0.1% of CH4 and 0.99 of N2. Okay, now you send this one to this one here. So that mixture you need to send to this one. So now you already know that the carbon percentage is only 0.1 percentage. So now the current will be produced here. So you note on that reading. So suppose it is generating 1 ampere. So 1 ampere is corresponding for 0.1 percentage. Okay. And similarly, next you go for 0.5% of CH4 and 0.95% of N2 and send this mixture to through this one here, and the current will be produced. Let us think that that current is 2 amps. Now this 2 amps is will be corresponding by 0.5 percentage. So see, like this you need to generate the data until the desired range you want to have. Okay, the desired range means what? So usually the concentration of THC in IC engines may not exceed more than 15 percentage to 20 percentage. So up to 20 percentage of THC you need to make this. Suppose if you are going for some other applications, something like a petrochemical refinery industries, then the THC concentration will be much higher. So you need to take some extra range also. So the calibration all depends upon what kind of application you are using. So for IC engine applications, probably 15% will be enough. Okay. So what is the advantage of this method? The main advantage is that the response of the response of FID is very fast. So it's order of 1 millisecond. Okay, so it can be used even to study the cycle to cycle variations in the combustion phenomena of IC engines. Okay, so what are the cycle to cycle variations? You please read yourself. So it's not there on syllabus, but you please read yourself in the from the Google or refer some other textbook. Okay. Also, the system is very robust. Okay, what the main disadvantages? The main disadvantage from here is that this method will not distinguish between different hydrocarbons. Okay, so suppose the exhaust gas will be having CH4, C2H6 and C3H18, C3H10. So this method will not distinguish all this one. It will give only one reading together of this one. See, this method is only sensitive to carbon atoms, not the mixture of the CH4 or C2H6. It's only detecting the carbon atoms. Okay, so in that way, we are not able to differentiate between individual hydrocarbons. So that way the name is given as total hydrocarbons. Okay, the name itself is indicating that you are measuring the total unburned hydrocarbons, not individual hydrocarbons. So next we'll go for the measurement of the CO. Okay, so it is NDIR, so non-dispersive infrared absorption method. Okay, so if you read gas chemistry, the CO will absorb the infrared radiation at particular wavelength. Okay, um, so when you are sending infrared radiation through CO, it will absorb that infrared radiation and it will increase in its energy. Okay, so the increase in energy will reflect in the pressure also. Okay, now the increment in the pressure can be taken as the representative of the amount of CO present in the sample gas. Okay, so when it is absorbing infrared radiation, there is increase in its energy. So hence there is increase in the pressure also. So now the increase in the pressure is the direct representation of the concentration of CO in the sample gas. Okay. Now there is a problem in this one because the exhaust gas will consist of CO2 also. Okay. Now the wavelength at which the infrared absorption will be occurring in CO2 are approximately same. Okay, both are very close to 4.4 microns. Okay, so now what will happen when you are trying to measure the CO concentration? The readings will get interference from the CO2 also. So you need to segregate this one. So this can be done using what are known as filter cells. Okay, so this we'll discuss in the next slide. So you should remember that we need to take precaution to avoid the interference that is coming from the CO2. Okay, so now what are the main parts here? As I said earlier, so there should be a unit for the generation of the infrared, and then there should be one electrical circuit to measure the pressure difference, and then you should have the cells where you can send the exhaust gas, where you can keep the reference cell, and where you can keep the filter cell. Okay, so this is the diagram. So we'll start from this side. So here S1, S2 are representing for the source for the infrared radiation, and S2 is the motor which will be supplying the motor which will be rotating this wheel. So S3 is what? Shutter wheel, which will be rotating the shutter wheel. Okay. The power supply for this entire unit is coming from the a power unit from here. Okay. Now you can see that this right hand side is known as the detector cell or the receiver cell. So this can is known as a detector or the receiver cell. Okay. So these two units are known as the measuring cell. Okay. These are known as a filter cell. Okay. So in the measuring cell, we'll be sending the sample gas to which you want to measure the concentration of CO. Okay. In the reference cell, so you'll be putting air. Okay. So this reference cell will be filled with the air. Okay. The filter cell are used to avoid the interference from the CO2. So we'll be putting CO2 in these two cells. Okay. In the receiver cell or the detector cell, we need to put the concentration of the gas to whom you are measuring. So it will be filled with the CO. So we are trying to measure CO concentration. So we'll be putting a CO here. Okay. Now we'll discuss about the operation. Okay. In the operation, what we'll do in the receiver cell, right? First you fill up the CO. Okay. In the receiver cell, first you fill up the CO. And in the reference cell, which is M2, you fill the air. And the filter cell, you fill the CO2, both up and down. Here, the measurement cell will be empty. Okay. Now you send the infrared radiation. Now what will happen? When the light is infrared radiation is going through this in this direction, first it will be obstructed by the CO2 in the filter cell. So the CO2 will absorb the infrared radiation at its own wavelength. The remaining light will be passed on to the reference measurement cell. Here nothing will be there, so there won't be any absorption here. Now the light will be passed on to the reference cell. So here the CO, whatever it is there in this cell, will absorb the infrared radiation, as a result of which the energy will be increasing and the pressure also will be increasing. So that pressure will be picked up by the circuit. Okay, now you connect the measurement cell to the exhaust gas. Okay, a sample of the exhaust gas will be allowed to pass on through this measurement cell and it will be leaving this one. Now what will happen? Now the infrared radiation will be continuously sending. So here it will be passed, and then when it is coming here, since CO is there in this exhaust gas, some amount of infrared radiation will be absorbed by the this CO. Okay, and the remaining amount will be will be sent to here in this one. Okay, now CO is there here and CO is there here also. So these two will be taking the this light at only fixed wavelength. Okay, so certain amount of energy will be taken by the CO that is present in the exhaust gas here. So the left out amount of infrared radiation at the same wavelength will be passed on to the reference cell. Now what will happen compared to the initial case, less amount of energy came here, so the increase in the pressure will be lesser here. Now this delta P will be picked up by this electrical circuit. Now how much amount pressure rise you are seeing here will be actually representing you how much amount of CO that is there in the exhaust sample that has been passed to the measurement cell here. Okay, so this is the principle here. Okay, okay, this is what I said. So we'll okay. Now filter cells. So what the purpose of filter cell means? So we in the filter cell we are adding CO2 and it will absorb the IR corresponding its own wavelength. Okay. The remaining IR continue to radiate to the sample cell at different wavelengths. Okay. Now CO2 in the exhaust gas in the sample cell will not absorb IR. Okay. In this way, the interference of CO2 is eliminated with the help of filter cell. Okay. So in the reference cell, we are using air because we want to make the comparative measurement of the absorption signals. Okay, so this is the reference cell. The reference cell will be used for the standardization of the signals about the how the absorption will be occurring here. Okay. So the what is happening in the filter cell means, see there is a CO2 here and in the exhaust gas also CO2 is there. Okay, so when the IR is coming from here, so the wavelength that is corresponding for the CO2, that kind of infrared radiation will be absorbed here itself. Okay. Now the water CO2 may be here that cannot absorb the infrared radiation because the wavelength at which it has to absorb is already been done by CO2 present in the filter cell. So although CO2 is there in this cell, it cannot take infrared radiation because that wavelength corresponding to this one is not available in the infrared. That already been used by the CO2 present in the filter cell. So in this way, we are able to segregate the effect of CO2 in the exhaust gases. So the filter cells are very important in this measurement. So the calibration is similar to what we have done for the FIT method. So here also we need to have some understanding of the changes in the delta P and what it is corresponding for the CO concentration. Okay. So to do this one, what we'll do? So gases with a known amount of species concentration will be allowed to pass through the sample cell, and the pressure difference need to be marked for the calibration. This meaning is that suppose that I will take a mixture of N2 plus CO. Okay. So I will take a sample of N2 plus CO with a CO percentage, maybe 1%. So I will send through this one. Okay. Now when you are sending IR from here, it will be detecting one delta P, and it will be picked up with this electric signal. Now you know that this sample gas is consisting of 1% of CO. So suppose that the pressure difference what you are getting one millibar. Suppose that it is coming 1 millibar, then 1 millibar is corresponding for the 1% of the CO. And next what you will do, you slowly enhance the concentration of the CO in the sample gas to what you want to have. So next time you send 5% of the CO, so that will be 5% of CO plus 95% N2. So this mixture will be allowed to pass through the cell and then measure the difference in the pressure. So like that you need to continue and get the calibration chart actually. So it is means that, so when you are having a 1 millibar pressure increase or pressure difference, then that should be corresponding for 1% 1% of CO like that. Okay, after finishing all this activity, so this will be taken as a reference for the reference for the readings. Now you send the exhaust gas actually here from here. Okay, suppose that in the exhaust gas the reading is coming to be 2 millibar, then the 2 millibar, so you go back for your calibration chart and I pick up the pressure difference that pick up the uh, concentration of CO that is corresponding for the 2 millibar pressure signal. Okay, in this way you have to use the calibration and use the, and this calibration chart should be used to measure the CO. Okay, so that's about the measurement of CO. Next we'll go for the measurement of the NOx. So it is a chemiluminescence method. Okay, what the principle here means, when NO reacts with the ozone, right, an activated NO2 will be liberated. Activated NO2 will be liberated. Okay, now when this activated NO2, the meaning of activated chemical species means the chemical species is not stable actually. It will not remain at the same chemical nature. Okay, so it has to rapidly find out some other chemical reaction, convert it to some other chemical stable state. Okay, now what we'll do, so this activated NO2 will collide with the O2 liberated from the previous reaction and changes to stable NO2. Okay, so in this form, when it is converted into stable NO2, there will be an emission of the light in the form of the photon. Okay, now the amount of photons that you have been liberating through this reaction will actually represent you the amount of NO that is there in the sample gas. Okay, so these are the reaction. So NO plus O3 gives rise to NO2 star plus O2, where the star will indicate to that it is chemically very active or unstable species. Okay, now this NO2, right, will collide with the O2 that formed in this reaction and convert into NO2 plus O2 plus photon. Now this photon need to be measured, and this amount of photon that has been come through this reaction will be proportional to the amount of NO in the exhaust gases. Okay. Um, so as we can see here, the exhaust gas usually from IC engines will be consistent of NO2 also. Okay, so now if exhaust gas will consist of NO2, then you will be having interference of the results because of the NO2. Okay, so the NO2 should be generated only through this reaction only. If the sample gas will be consisting NO2, then it will be difficult to distinguish between NO and NO2. So to avoid this one, what they will do, usually before sending into the this measurement zone, the NO2 in the exhaust gas will be converted into NO. Okay, then what will happen? So you don't have any NO2; it's only purely NO now. So there won't be any problems of the in the measurement now. But what is the difficulty here? So you are not able to measure individually the concentration of NO and NO2. So you'll be getting total summation of NO plus NO2, which popularly known as the NOx. So this is what the meaning of NOx. So if you are working for the BS4 engine development, so this is not an issue. But suppose if you are looking for the BS6 limits, then it is an issue. So for the BS6, most of the time we have to use SCR. So you already discussed in SCR. So in the SCR, in the chemical reactions, the percentage of the NO, NO2 has a dominant effect on the performance of the SCR system. So we need to measure exactly what is the proportion of NO, NO2. Accordingly, we have to inject the area. So until you are working with the BS4 engine development, it's not an issue. But the moment you are going for the BS6, so it's not straightforward. So you should have some understanding of what is the NO NO2 ratio also. Okay. But presently this method will give total in together NO plus NO2 concentration. Okay. So coming to the parts, as I said earlier, so you should have the ozone generator because that is the main species in the reaction. Then a NOx converter to convert NO2 into NO, and then the reaction chamber and photon measurement system, and of course pump and regulators and flow meters to control the flow of ozone and the sample gas. Okay, so in this one, so we'll start from here actually. Okay, so the air is coming from here and it is going to the ozone generator. Okay, so we are generating ozone using the atmospheric air here. Okay, so this P will be current representing the pressure regulator. Okay, so whatever you are generating ozone here, so that we are sending to the reaction chamber. Okay, now so the sample gas is coming from here. Okay, from the sample gas, so there is a NOx to NOx converter. So in this place, what you are doing, so you are converting NO2 to NO. After converting, you are sending through this three-way wall into the reaction zone. So by the time the sample gas is coming from here, there won't be any NO2. It will be full of NO only. But when you look at here, so it will be consisting of NO2 plus NO. Okay. So the remaining all the systems are for the flow measurement and the pressure regulations. See, since some reactions are occurring here, so you need to maintain proper control of the pressures. Okay. So if you see here in all these measurement systems, right, there's a pressure regulator is there, flow regulators are there. So we don't have finite details or the calculations or design about the setups. Okay. So the moment you are falling into design of this setup, right, and the pressure is going to be a very critical parameter. Okay. All this accuracy of this pressure, accuracy of all this measurement will depend upon at pressure, at which pressure we are doing, what are the flow rates. So all this stuff will be going. So that's why in all these measurement systems we are having the flow meter as well as the pressure regulator. Okay. So now in this is the way the reaction zone will be occurring. So here the ozone will be reacting. So NO will be reacting with ozone and the photon will be liberated and the amount of photon will be calculated or the measured in this photomultiplier tube here. And the calibration, it will be similar to NDR method. So first you need to send known amount of concentration of NO and find out the amount of photon that is coming and make a calibration chart. So now the last topic, so we'll be discussing about the smoke measurement. So as I said in the first slide, so smoke can be measured two way. The first one is the comparison method. So this measurement is based on the comparison with respect to a reference. So in principle, it is developed for the qualitative measurement. The example is Ringelmann chart. The next one is obscuration method. So it is a direct method. So it can be used for the quantitative measurement. Example is Bosch smoke method. So first we will discuss about the Ringelmann chart. So usually this chart will consist of 5 gray color charts. So each chart varies in terms of intensity of the gray color. Okay. So 0 chart will consist of all white lines, and the first chart will consist of the black line of 1 mm thick and 10 mm apart, so that white space will be of 9 mm square. Okay. The second one will be consisting of a 2 mm thickness of the black lines. Third one will be consisting of 3.7 mm thick black lines, and fourth one is consisting of 5 mm black thick lines, and the fifth one will be consisting all black lines. Okay. So here you can see this one. So this 1, 2, 3, 4 charts are given here. Okay. So as you can see, as we are moving from 1 to 4, the thickness of the black lines is increasing on a white background. So all these charts are made on a white background. Okay. Because you can see that when you are going from 1 to 2, the thickness of these lines is increasing, and similarly from 2 to 3, thickness also increasing. So now we have 0 on this side and 5 on this side. So 0 will be it does not have any black lines, so it's completely white. On the other hand, the fifth reading or the fifth chart will be completely black lines. Okay, so these are known as the Engelmann charts. Now, how can you use this one to measure this one smoke? Okay, so what you need to do is that suppose that a stack is there and whose smoke you want to measure. Okay, so you have to keep a distance from the stack nearly 10 meters, and you take these 5 charts and try to see which chart is resembling closely with the exhaust gas or the effluent. Okay, so you have these 5 charts, right? So you keep some distance. Your eye level should be sighting the smoke, and you try to find out the best match between the Engelmann chart and the visibility that is coming from the smoke. Okay, you pick up that smoke, you pick up that Engelmann chart. Now that number of that Engelmann chart will indicate you the density of the smoke present in the exhaust gas. Okay, so this is the principle. Okay, so this method is extensively used in the boilers and the coal mines. Okay, so if the smoke is below Engelmann chart number 2, then the error expected to be significant. Okay, so mostly this method can be used for the 2 to 4. Okay, so just see here, if you see these effluents, so it is light gray, it's mild gray, it is severe gray. So you need to make comparison. You see that this gray is matching with this map. Probably this is the closest match. So then the smoke present here is Engelmann chart 1. Okay, and if you see here, this matching a little bit closely with this number. So the smoke number here is Engelmann chart 2. And if you look at here, so this is closely matching with this one. So the chart number will be 3 for this one. Okay, so this is how you need to measure. So now it is all depends upon individual judgment also. Okay, so suppose you have something between that falls in between 2 and 3, then the judgment will depends upon the person to person individual. So that's why I told in the beginning, it's not exactly quantitative, it's a qualitative measurement only. Okay, so now we'll discuss about opacity. So opacity is a measure of impenetrability to visible light. So opacity means, probably you would have studied in plus 2 chemistry or the physics. So it means that, so it is a measure of the impenetrability to the visible light. Okay, so when the opacity high means the obstruction to the light is more, and when it is low means obstruction to the flow is low. Okay, so when the smoke is there in the exhaust, it obstructs the light, and so opacity of the gas is an indication of the density of the smoke in the exhaust. Okay, suppose you take exhaust gas and you send the light and try to measure the opacity. Okay, so the presence of CO, NO and THC will not change the opacity of the gases. So those are not sensitive to the exhaust gases, but the smoke is sensitive to the light. Okay, so it actually obstructs the light and so result in opacity for the smoke level. Okay, now that the opacity of the smoke can be taken as a representation of the density of the smoke in exhaust gases. Okay, so when I say that opacity is 0 and no smoke in exhaust, because there is no obstruction to the flow, obstruction to the light, so that means that the exhaust does not have any smoke. And on the extreme other end, when I say that opacity is 1, the light is not at all going through that one, it is complete obstruction. That means that the level of the smoke in the exhaust smoke is extremely high. Okay, so which indicates that it is a poor combustion. Okay, now people made some establishment, some correlation between this opacity and Engelmann chart number 1. Okay, so the first chart will be corresponding for a 20% opacity, and the second chart will be corresponding for 40% opacity, and third chart will be corresponding for 60, fourth it's 80, and fifth for 100 opacity. Okay, that means that, so if you are seeing a smoke exhaust gas, so you try to measure something like this, and if you see that the opacity, the Engelmann chart is 5%, 5 number, then the opacity will be 100%, and which indicates that the exhaust is completely considered as smoke, and the combustion inside the cylinder is extremely bad. Okay. Okay. Next we'll go for Boss smoke meter. The principle is that, so you will be having a filter paper. Okay, and you will allow the exhaust gas to pass through this filter paper. Okay, so what will happen now, the smoke, no, whatever the exhaust gas will stick to this filter paper. Okay, now because of the sticking or adherence to the filter paper, the reflectance of the filter paper will be changing. Okay, now you measure the reflectance before sending the exhaust gas, after sending exhaust gas. Now the difference between reflectance of this filter paper will indicate you the density of the smoke in the exhaust. Okay, so this is a simple principle. Okay, now again you require some kind of calibration. Okay, so a clean filter paper of 0 will be representing you 0 smoke in exhaust gases, and similarly a number of 10 of the reflectance, change in reflectance of 10 will indicate you that the case is consisting of excessive or unacceptable smoke level. Okay, so this is a diagram. Okay, as we discussed previously, so you need to measure the reflectance of the paper. So you need to measure the reflectance of the filter paper. Then second one is that you should have a pump to take the sample of the exhaust gases. Okay, so this is a total unit. Okay, so we are starting from the top. So this is a sampling connection, and this is a filter paper, and this is a piston pump. So this is a pump to draw the exhaust sample to this one. Okay, remaining all units will support this measurement. Okay, so the enlarged view of this one is shown here. Okay, so inside this one is the filter paper. So this is exactly we are at this location. Okay, so above this one, so this another photocell is there. So the reflection that is coming from, so the light, so see, we are sending light through this lamp, and the rating is given 3.8 volt and 0.0 ampere. So the light is falling on this filter paper. Now it will be giving the reflection. Okay, so when you are sending the smoke here, the strength of this reflection will be changing. Okay, so that reflection will actually tell you the reflectance of the paper here. Okay, this one, the operation is quite simple here. So we will be sending the sample gas through this connection here, and the gas will be allowed to pass through this filter paper. Okay, so once it is after completed passing through this entire system, so using this method we will be getting the reflectance of the method. Okay, now the reflectance need to be measured on a 1 to 10 scale using the calibration what you have done. Okay, so this is the end of the this topic, measurement of emissions. So most of the data I have taken from, all the diagrams I have taken from the internal combustion engines from V Ganeshan, which is actually a reference book. The material, operation, everything I have taken from this textbook, Introduction to Internal Combustion Engine, Richard Stone. Okay, so you can refer any of this book, but the diagrams I have taken from internal this book only Ganeshan. So you need to refer this book. For better understanding, you can refer better understanding of the operation principle. You can refer this book, so Richard Stone. Okay, so I'm stopping the class now.